All right, welcome to Unit 5. So Unit 5 is going to do a lot of Algebra 2 review to prepare us to when we get to these things called limits of functions. So let's first talk about what is a function. So the definition of a function is that every input has a unique output. That means that if you plug in a certain x value into a function, only one y value can come out. So let's look at this. This is a relation. It's a set of ordered pairs. So each ordered pair is an x and y. So if I plug in 1, I get 2. If I plug in 2, I get 3. But then if I plug in 1, I then get 3, which is a problem. I cannot plug in the same x value and get out two different y values. So this is not a function. Number 2 is we're looking at an equation x squared plus y squared. So sometimes graphs are helpful. So like this graph, you should recognize this being a circle of radius 2. So I'm going to draw a circle, make sure that the radius is 2, and it looks like that. So with graphs, what's nice about functions is that we have this thing called the vertical line test. If I can draw a vertical line anywhere on this graph and it hits the graph more than once, it is not a function. So that's the vertical line test. And we can just abbreviate it VLT if we're ever asking you to explain why. VLT just stands for vertical line test. Again, graphs are always good to look at. Points are good to look at. Anything like that can tell if a function is, if a relationship or a graph is a function or not. All right, so let's review domain. Domain, we usually like to give it this kind of notation. And domain, by definition, is all possible inputs, or in most cases, x values. So we ask ourselves, okay, well, in this function here, which is 2x plus 3, which is a very familiar equation, it's a linear function. And if you think about a linear function, a line that just, goes off, to infinity and negative infinity, to the left and to the right, up and down, it just always goes around. So what values of x can I put into this function? Well, any value of x. So we have special notation that says that all numbers are accessible in this, all numbers are domain. So we call this all real numbers, and that's the script R. All right, what about this next one? Well, this next graph is called a rational function because it's a fraction. But we have to be very careful with fractions. The one thing that a lot of students remember is that the denominator cannot equal 0. So dividing by 0 is not possible. So in order for us to find the domain, we're going to set the denominator equal to 0 and find out that x, when x is negative 3, it creates a problem in my graph. I cannot plug in negative 3 because then I get 0 in the denominator. I can't divide by 0. So for these notes and for these set of problems, we're just going to stay very basic and just say that x doesn't equal to negative 3, which we are assuming that we are talking about every x value in the real number system. There is notation out there that could be very specific of all of that, but for now, we're just going to say, it's all the x's except for negative 3. Well, then what if we have a problem that looks like this? Well, this is also a rational function. The denominator cannot equal 0. So we ask ourselves, okay, what values of x's would create 0 in the denominator? Well, if you put x plus 3 equal to 0, just like what we did, that's negative 3. So x can't be negative 3. But then we also have x minus 2. So if we set that equal to 0, we get that x cannot also equal 2. Again, we are assuming that all of our x's in the real number systems exist except for negative 3 and positive 2. Oh, what about this one? This one looks a little bit more complicated, but it's still a rational function. The denominator still cannot equal 0. So we set this equal to 0, set this denominator equal to 0, get x squared equals negative 4, and if you square root both sides, can I square root the negative 4? No. So Can this denominator ever equal 0 if it's x squared plus 4? No. X squared plus 4 will always give us positive numbers bigger than 0. So I don't have any x's that will cause any problems. So we're going to say that x is all real numbers. Ooh, the square root. Well, in functions, we're talking about real numbers. So we need to make sure that we're always getting real numbers. Well, the problem with square roots is that we can't square root negative numbers. So what we're going to do is we're going to set the inside of the radical, which is a radicand, and we're going to set that equal to greater than or equal to 0. That's how we're going to figure out what values of x's can I plug into this and still get a real number. So you add 1 on both sides, and we get that x has to be greater than or equal to 1. Again, it is safe to, we're assuming that we're talking about every x value in the real number system, but for this one, we're restricted to plugging in 1, because then if we plug in 1, we get 0, square root of 0, 0, that's fine. And then anything bigger than that. If I try to plug in anything less than 1, you end up getting negative numbers, and you can't square root those and get real numbers. All right, what about this one? Well, we're still going to set this radicand to be greater than or equal to 0. But the problem is that I have two x's. There's not a way for you to simply just set each of these factors greater than or equal to 0. So when we have these polynomial inequalities, we like to do the wave. So the wave is just a quick way for us to tell where a function is positive or negative. So we need to figure out our critical points. So what values make this function 0? Well, -2 and +2. Since the leading coefficient of each of the x's are positive, we're going to start at the top right-hand side of our number line. Since 2 is a single root, we go through and then get back to -2. -2 is a single root, so we go through that, and that's what our wave looks like. So in this inequality, it's greater than or equal to. So since it's or equal to, these dots are going to be closed. Since it's greater than, we're talking about where is this function positive? Well, it's positive to the right of +2 and to the left of -2. So depending on what kind of a fan you are of set notation and stuff like that, if you love interval notation, which is -∞ to -2, square bracket, but then a parenthesis on -2, or 2 with the close or square bracket off to +∞ with that has a +∞ that has a parenthesis. Or I kind of just like inequalities. We're going to say that x is less than or equal to -2, or x is greater than or equal to +2. If you try to plug in anything in between -2 and 2, you're going to get a negative number inside the square root, and you can't square root negative numbers. What about this one? Well, this is the same idea. We have this radical and this radicand that's inside of it, and the idea of square rooting something and for it to have an answer, a real answer, the inside has to be greater than or equal to 0. Well, this is also kind of technically a polynomial. We have multiple x's, so we're going to do the wave. Just like the previous problem, we're going to have critical points at 2 and at -2. Why there? Well, -2 creates 0 on the top, which makes the function 0, and then +2 makes the denominator 0, which we can't have the denominator. So these are values of x's that are very important in this equation. Now, the inequality is greater than or equal to, but they're not both closed circles. If you plug in -2 in for x, that's okay to do because then you get 0. But if you plug in +2, this function's undefined, so we're going to have to put an open circle at +2. And just like the previous one, the leading coefficients are both positive, so we're going to start off at the top right and then go through each of them because they are single roots. And we're talking about greater than or equal to or greater than, so that's above the number line but bounded by the wave. So our inequality again is x is less than or equal to -2, or x is greater than 2, not equal to. So be very careful with what you're doing. All right, so that's domain. Range, on the other hand, is a little bit more, it should be a little bit more visual to people. And And the reason why is because the range is all the possible outputs of a function, or in most cases, y values. So these first three functions here are the absolute value function. So what I did quickly before I started recording is I drew each of those graphs. So the absolute value function is this kind of V-looking graph, which if I ask you what the domain is there any value of x that you cannot plug in here? Can you absolute value every number? Yes. So the domain would be all real numbers. However, you don't get out every y value. You only get out positive values or 0. So we're going to put y is greater than or equal to 0. There might be some places where you use function notation like f of x is greater than or equal to 0, but it doesn't matter. Just y is greater than or equal to 0. Well, if you remember back to transformations, the absolute value of x plus 2 is shifting the graph to the left to -2 because that's what makes that 0. So if you look at the graph, still plug in any values of x's, but I'm not asking domain. The range is still starting at 0 and going up. So y is greater than or equal to 0. I didn't manipulate my output at all. I manipulated the input. Unlike the next problem, I am manipulating the output because that plus 2 is on the outside of the absolute value. So I shift my graph up 2. So now the lowest y value it gets to is 2 and everything bigger than that. So y is greater than or equal to 2. Then the next three functions are the square root functions. So the square root function kind of looks like this. If you want to plug in values, you can. If I ask you domain, just like what we did on the top problems, the input of square root functions have to be positive or 0. Well, what ends up happening is if you plug in numbers that are positive or 0, you're also going to get numbers that are positive or 0. So all of our output for the square root function is greater than or equal to 0. If I manipulate my input and shift it to the left one, doesn't affect my output, still greater than or equal to 0. However, the next one, I'm shifting the graph to up. So now the lowest value of y that can come out is positive 1. So y is greater than or equal to 1. Now, sometimes you might not know what a graph looks like. And sometimes you have to, do some things. So this x squared causes a problem. So this creates this very, very specific graph. And what I'm going to do first is kind of manipulate it a little bit. I'm going to take f of x and change that to y. I'm going to get rid of the square root by squaring both sides. So y squared equals to 4 minus x squared. And this is starting to look a little familiar. If I add the x squared over, you get x squared plus y squared equals 4. This is the same kind of circle problem that we had above when we asked about functions. However, since we were solving this for y and it's a square root, this is only the positive version of that circle. So I didn't draw this beforehand, but so if I go, so the radius is 2, but it's only the top half of that circle, so it's only this. So you have to be very careful with what I'm asking. If I ask for a domain, the only x's that you can plug in are from -2 to 2. But all the y values go from 0 to 2. So how do you write that? In any way you want to. If you want to do interval notation, square bracket 0 to 2, square bracket, that's fine. If you like inequalities like I do, 0 is less than or equal to y is less than or equal to 2. So this is going to be a very important graph for you to think about and know. So semicircles are of the equation, or let's use a fancy notation, f of x equals the square root. Well, if it was x squared minus 4, that would be a completely different graph. So this semicircle is r squared minus x squared. If the square root's positive, it's the top half. If it's negative square root, then it's the bottom half. But it can't be the left half or right half because then it wouldn't be a function. That's not possible. So now this equation, recognize it again. If that's in any other order, x squared minus r squared, it is not a semicircle. So maybe undo something to it, see what kind of graph you originally get, and see what happens. But these are the equation of semicircles. Well, this isn't a square root, this is a rational function. And if I asked you to find the domain, that would be a different question, but we're asking for the range. So what does this graph look like? Well, if I don't really know what this looks like, so what do we always do if we don't know what a graph looks like? We don't want to look at it. Plug in points, make a table. What are some values of x's that you would like to plug in? I think 0 is always a nice number to plug in. If you plug that in, you get 1/2. So that means on this graph, I'll have a point at 0/2. Then 1 is a nice number. So if you plug in 1, you get 1 over 1 squared plus 2, so that's 1/3. What happens if you plug in -1? Well, you get the same thing of 1/3. And if you plug in maybe positive or -2, what do you get? A sixth. And you can keep going. And you can kind of ask yourself, like, when we did limits of sequences last unit, like, what's going to keep happening if x just keeps getting bigger and bigger and bigger? Well, this fraction is going to keep getting smaller and smaller and smaller. It'll never actually get to 0. So we're going to have an asymptote here. And our graph is just going to get smaller and smaller and smaller and smaller, even if you start plugging in negative numbers. So this is kind of what the graph looks like. And again, it'll never be 0. It'll be always positive, but the maximum it ever gets to is 1/2. So we're going to say that our y values are between 0 and 1/2, not including 0, but including 1/2. And again, the best way to kind of figure out what this looks like is by plugging in numbers, graphing it, and see what happens. So those were all range questions. If you have any questions, please let us know.
All right, welcome to week 9. Well, we're going to start off talking about here are composition of functions. It's when we take functions, and sometimes multiple functions, and we evaluate them at certain values or plug in different expressions into them, and then we can do any kind of operations with them. Like here, we're going to plug in 2 in for f, 2 in for g, and then multiply them together. Another way we could write this is putting f and g together. So this is saying f of g at 2, or f times g at 2 as well. So that just means the exact same thing. You're plugging in 2 into each one of them and multiplying together. So when you plug in numbers into functions, make sure that you're plugging it in for every x that you see. So 2 squared minus 1 ends up being 3. G at 2, we have 2 times x, so 2 times 2 plus 1 ends up equaling 5. So we're just going to take what we got for f of 2 and multiply that with what we got at g at 2 to get our answer of 15. So what about this here? This is telling us to take g of 2 and plug it into f. Well, we already figured out what g at 2 was. That's 5. So g at 2 is 5. So now I'm just going to plug in 5 into my function f. So 5 squared minus 1 is 25 minus 1, which is 24. Well, it does matter what order you're doing this in. If we're doing g of f at 2, that means I'm figuring out what f at 2 is and plug that into g. Well, f at 2 we figured out earlier was 3. So all I'm going to do now is figure out what g at 3 is. So 2 times 3 plus 1 ends up being 7. Well, like I said, we can plug in numbers or we can plug in other expressions. So if I'm going to plug in x plus 1 into f, so every x that I see is going to change to x plus 1. So x plus 1 squared minus 1. Now make sure you follow directions, and if you need to simplify this further, you should FOIL this out. And please do not tell me that that's x squared plus 1, because you are missing a middle term of 2x minus that 1 that's on the outside. So if we completely simplify it, we end up getting x squared plus 2x is our final answer. So if we have a variable inside of this function, our answer is going to be some kind of expression. If it's plugging in a number, you should get out a number. This next thing you're going to see a lot this semester and also in calculus of plugging in x plus h in for x, subtracting f of x, and dividing by h. So make sure that you are showing all the steps when you do this type of problem. So I'm going to take my function x squared minus 1, and I'm going to plug in x plus h. And you're going to get into more complicated functions later on where you're going to have multiple x's. So make sure that you're doing that for every single one of them. Then we're going to subtract f of x, which is x squared minus 1. And since it's in it, a binomial, we need to make sure that it's in its own parenthesis. And then we're going to divide that all by h. So let's fully simplify this problem. So x plus h squared is going to be x squared plus 2xh plus h squared. And then we have that minus 1. And I'm going to distribute the negative into that and then divide it all by h. Well, I can simplify this top. The x squared minus x squared cancel each other off. The minus 1 and the plus 1 end up canceling off. And to help out, I'll just cross those out. So you're left with 2xh plus h squared all over h. Well, each term has an h, so if I divide them all by h, you end up getting left with 2x plus h.
So that previous question, we dealt with a kind of parabola, quadratic function, and a linear function, which both has no restriction on our domains. But what if we do a composition when we're dealing with something that has restrictive domains? So what we're going to do is we have f of x is this and g of x is that. So I'm going to find the domain for each of these. Well, the domain for this function here would mean that the radicand, the thing on the inside of the square root, has to be greater than or equal to 0. Well, if I'm going to solve this, since we have multiple x's, I'm going to use the wave. The value of x that makes the numerator 0 is 0. What makes the denominator 0 is 1. Well, since we're square rooting, this fraction could be 0, so my answer could be, or my value of x could be 0, but the denominator cannot be 0, so it can't be 1. And since we have a negative x leading coefficient, we start off on the bottom right. They're single roots, so it goes through each of them. So then the domain for this is greater than or equal to, so everything here. So that means the domain for our function f is simply just going to be 0 is less than or equal to x, which is strictly less than 1. Well, g of x is just the square root of x, so that means the domain for that would simply just be that the radicand at x has to be greater than or equal to 0. Well, if we're going to put these two functions together as one, what I need to do is I need to AND these two domains. So I need to figure out when is x less than or equal to, or greater than or equal to 0 and less than 1, and when is it x is greater than or equal to 0. So again, we're looking for the AND between these, the intersection of these. So I'm going to straighten out this line a little bit because it doesn't look very straight. I'm going to put 0 and 1 on here. And what I'm going to do is above the number line, I'm going to draw each of those. So x is between 0 and 1, including 0 but not including 1. And then x is greater than or equal to 0, looks like this. And if you're looking for the AND, you're looking for the overlap of the two, which ends up being everything between 0 and 1, including 0 but not including 1. So the domain for most of these function compositions that we're going to do is going to stick with this same exact domain unless we restrict the domain even further. So if we have f plus g of x, this does not say add f, add g, and then multiply by x. This, in other words, is saying you're taking f of x, g of x, and adding those two together. Well, f is x over 1 minus x inside the square root. G is just simply the square root of x, and we're adding them. So that's it. I'm going to fix the square root a little bit better. There we go. And that's honestly as much in this class that you need to simplify this to. But remember that we're not just talking about the domain of f or the domain of g. We're doing the intersection of the two, which we found out is this. So then you ask yourself the question, it's like, okay, well, in any of this scenario of adding x over 1 minus x or the square root of x, do we restrict our domain even further? No. So that's our answer. Well, what happens if we have fg of x? Well, again, it's not multiplying fg and multiplying by x. We're taking f of x, g of x, and multiplying them together. So then we end up getting, well, instead of the square root of x over 1 minus x, I'm going to rewrite it as square root of x over the square root of 1 minus x for the sake of notes. G of x is just the square root of x. So if you multiply the top times the top, the bottom times the bottom, well, root x times root x is just x. And then the square root of 1 minus x times 1 is just the square root of 1 minus x, which you could rationalize if you want to, but you don't have to. But remember that our domain got restricted to this. And then you ask yourself one last question. It's like, well, wait a minute. Did I cause any more restrictions on my x's? No, that's it. Well, what about this next one? This is the same thing as taking f of x and dividing it by g of x. Well, f of x is the square root of x over the square root of 1 minus x, which I'm just rewriting for the sake of notes, and then dividing it by g of x, which is just root x. Now, the reason why I wrote it separately like that is because what I'm going to do is I'm going to multiply the top and the bottom by the reciprocal of the denominator. So multiplying the top and the bottom by 1 over root x, which ends up canceling these out. So we end up simplifying this to 1 over the square root of 1 minus root x. And that's it. That's our answer. And then our domain is x is between 0 and 1, and including 0 but not including 1. But then you ask yourself the question, did I cause any more restrictions on x? And the answer is yes. Right here, since we're dividing all of this numerator by the square root of x, we tell ourselves that, oh, well, we can't divide by 0. So that means that this cannot be 0. Well, what makes that 0? Well, 0. So that means 0 cannot be included. So we're going to change our inequality to strictly between 0 and 1, not including either 0 and 1. So this is how you're going to end up restricting your domain even further, dependent on the problem. And it has to work for every single step of your simplification. All right, and this last problem here, it's an interesting one because what we're going to do is we're going to square f, square g, and then subtract them from each other. So f is this, all inside the square root, and then we're going to square that. And then we're going to subtract g, which is this, and then square it. Well, if you square a square root, they cancel each other off. So we're going to do x over 1 minus x, which, I mean, you could say that this is the simplest form, but it's not that difficult to change this to one fraction. So what I'm going to do is I'm going to make this a fraction and multiply the top and the bottom by the common denominator, which is 1 minus x, and end up getting this all over 1 minus x, which we simplify the numerator. We distribute the negative x, and combine like terms, and you're only left with x squared over 1 minus x, which is the most simplest form of this. So what did we say our domain was that follows us through each of these problems? Because we start off fresh for each of these parts. And then you ask yourself the question at the last, like, did I restrict my domain any further? Well, here it's the same domain, no matter if I'm squaring it, same domain as earlier, no issues here, no issues there, no issues there. So that's your final domain. There was no more restriction on x throughout any of my steps of simplification. So this next question, we just added this recently to our notes. What this is going to review is something that we call even, odd. This is an Algebra 2 topic that you might have seen in our Advanced Algebra 2 here at Anderson. So since this question is asking to compose one function into the other, g of x into f of x, we want to make sure that we find the intersection of the domain. Well, for f of x just being the square root of x, the domain of that is going to be x is greater than or equal to 0, because we can only square root positive numbers and 0. X minus 5 to the 6th power is going to be just a parabola looking thing. It's going to be a U-shaped graph. There are no restriction on our input. So the domain for g of x would be that x is just an element of the real numbers. Well, if I'm going to do the composition of these two, I'm going to need to find where they intersect. Well, they intersect at x is greater than or equal to 0. So now if I'm just going to find the composition of these two, where I'm going to plug in g of x, which is x minus 5 to the 6th power, into the square root function of f, and get this. Uh, so how do I simplify this? Well, right now what we're doing was we're taking an even root of an even exponent, and we're going to end up getting an odd power. Well, in a scenario like this, we want to make sure that all of our answers come out exactly as they should. What this needs is that all of this is the positive version of this. If you're square rooting something, it's always going to be a positive answer, unless you're solving by square root. But we're not solving by square root here. We're square rooting a number, and any square root of a number is going to be the positive version. But if you were to cube any negative number that's inside of this, you're going to get something negative. So how do we make sure that that comes out positive? Well, we add absolute value. So that's what even odd tells you to do, is if you're taking the even power if you're taking an even root of an even power and getting an odd power to guarantee that your answers are always going to be positive, you have to add absolute value bars.